This is section 2.5 lesson video. What we're going to learn is how to write and graph inequalities, and then we're going to solve compound inequalities, and we're going to use compound inequalities to solve real-life problems. A compound inequality is an inequality that's formed by joining two inequalities with either the word and or the word or. The graph of a compound inequality with and is the intersection of the graphs of the inequalities. The graphs show the numbers that are solutions of both inequalities. So we're going to look at the first inequality as x is greater than or equal to negative or to equal to 2. Our boundary point would be 2. It is a filled-in circle because we have equals and it's greater than, so we shade to the right. Second inequality is x is less than 5. 5 is our boundary point and it's an open circle, and we shade to the left. So the values of x that meet both criteria, where x is greater than or equal to 2 and also less than 5, is the region in between the two boundary points. So when we combine these two, it's the intersection or where they overlap. So we say that 2 is less than or equal to x, which is less than 5 in between. So here's our boundary points, 2 and 5. 2 is included with the closed circle. 5 is the open circle. The graph of a compound inequality with OR is the union of the graphs of the inequalities. The graph shows numbers that are solutions of either inequality. So our first inequality is y is less than or equal to negative 2. Our boundary point is negative 2 with a closed circle because it's equal, and we shade to the left for less than. The second inequality, y is greater than 1. We have an open circle for 1, and we shade to the right for greater than. Our combined solution is the values of x that satisfy either of the inequalities. So we say that y can be less than or equal to negative 2, or y is greater than 1. So the combined graph shows the boundary point at negative 2 and shaded to the left with negative 2 filled in, and our boundary point of 1 with an open circle for not included and shaded to the right. So we have a compound inequality with and, where we have a solution where the x values meet both criteria. We have a union with or, where we can have either one or the other. So writing and graphing compound inequalities, we're going to look at these examples. We're going to write the sentence as an inequality. So we're going to go from verbal to symbolism. The first example we'll do is this: a number x is greater than negative 8 and less than or equal to 4. Our second example will be a number y is at most 0 or at least 2. The solution for a number x is greater than negative 8 and less than or equal to 4. So a number x is greater than negative 8 is written with the greater than symbol, and x is less than or equal to 4. So we say x less than or equal to 4 using the inequality symbol. Because x can meet both criteria, where x is greater than negative 8 and x is less than or equal to 4, then we can write this as a single inequality by putting the x in the middle. Negative 8 is less than x, which is less than or equal to 4. And when we write these, we always write them least to greatest from left to right, with the inequalities pointing to the left, which is the lesser value. So this is our inequality. Negative 8 is less than x, which is less than or equal to 4. Graphing it, our boundary points are at negative 8 with the open circle because we don't have the equal sign here. And the other boundary point is 4, and it's a filled-in circle. And then we'll shade in between because it's the intersection where x is greater than negative 8 and at the same time less than or equal to 4. B, a number y is at most 0 or at least 2. So if a number y is at most 0, it cannot be greater than 0. So we say that y is less than or equal to 0. Or y can be at least 2. So if it's at least 2, it could be more than 2. So we say y is greater than or equal to 2. So our inequality would be written as y is less than or equal to 0 or y is greater than or equal to 2. And graphing, we have our boundary point at 0, which is filled in circle because of the equal sign. Our second boundary point on the right is 2. It is also filled in. And then we shade in opposite directions. Because y is less than or equal to 0, we shade to the left, or y could be greater than or equal to 2, we shade to the right. Okay, you can solve now a compound inequality by solving two inequalities separately because we've seen that they are two separate parts. When a compound inequality with and is written as a single inequality, you can solve the inequality by performing the same operation on each expression. So we have two examples of a compound inequality because we see that the variable x is in the middle expression in both examples. In part A, or example A, we're going to separate it and have two inequalities. In example B, we'll keep it in this form and then solve it, performing operations to the left, the middle, and the right side. So part A, we're going to start by separating the inequalities. Sometimes we may need to be able to think about something that looks complex and simplify it. So we're going to write two inequalities, keeping the middle part as the expression that belongs to both inequalities. So we have -4 is less than x minus 2, and x minus 2 is also less than 3. So now we're going to solve each inequality using inverse operations. So for the first one, we will need to add 2 to both sides to get x by itself. Our second inequality, we will need to add 2 to both sides to also get x by itself. So it's the same operation. Simplify, and our inequality on the left becomes -2 is less than x. We keep the and x is, and the inequality on the right becomes x is less than 5, which we can now combine because the criteria for values of x meets both. X must be greater than -2 and x is less than 5. So writing it with the variable expression in the middle. Now let's graph it. We have our two boundary points. We will always have two boundary points with compound inequalities. So we have boundary point at -2, which is an open circle because we do not have an equal sign here. Our second boundary point is 5, also open circle. And then we shade the region in between on the number line because x can be any number that is greater than -2 and also less than 5. Okay, example B. Now we're going to solve this one by not separating the inequality. We'll keep it as one inequality. And we look at the variables in the middle. So we want to solve for x. We need to undo adding 1. So we're going to subtract 1 from the middle, but we'll subtract it from the right side and also from the left side. So in this case, whatever we do to the middle to solve for x, we're going to do for the left and the right side as well. And let's simplify. So we get -4 is less than -2x, which is less than or equal to 8. And now we still need to solve for x, so we will need to divide by -2. And when we divide each expression by a negative number, remember that dividing by negative, we have to consider that the inequalities need to reverse direction. We have to reverse the direction of the inequality symbol because we divided by a negative number. Remember, this also happens if you multiply by a negative number. So now let's continue to simplify. So -4 divided by -2 is +2, which is now greater than x, which is greater than or equal to -4. Now when we write the inequality, we always want the expression going from left to right, least to greatest. And right now we have the greater number on the left and the lesser number on the right. We need to flip it. So do the revolving door thing. We have -4 on the left, which is less than or equal to x, which is less than 2. We just took the whole expression and flipped it around because we want our inequalities to read least to greatest from left to right, with the inequality symbols pointing to the left side, which is the lesser values. And now we'll graph. We have two boundary points, one at -4, which is closed because of the equal sign. The other boundary point is 2, which is open. X is in between. This is and. X meets the criteria of being greater than or equal to -4, and less than 2. Our third example is solving a compound inequality with OR. So we're going to solve the inequalities 3y minus 5 is less than -8, or 2y minus 1 is greater than 5, and then we'll graph the solution. So starting with our inequalities, we're going to find the first step for each one. The one on the left, we need to add 5 to get y by itself. This one will need to add 1 to get y by itself. So we're using the addition property of inequality. And then we're going to simplify. So we will have 3y, bring down your inequality, which is less than 3. Over here, we're going to add 1. So we simplify, get 2y is greater than 6. And now the next step is going to be division for both of these. We're going to divide by 3 here, and we'll divide by 2y for the second one. This time we're dividing by a positive number, so there was no need to reverse the direction of the inequality. So let's simplify each one of these. We get y is less than -1. Bring down your or, y is greater than 3. So our solution is y is less than -1 or y is greater than 3. Now we want to graph this. Our boundary points on the left would be -1 with an open circle, and on the right, the boundary point is 3 with an open circle. Now we want to graph the solution. Y is less than -1, so that's going to be shading to the left, or y is greater than 3, so we shade to the right. So our values of x could be either less than 1, or the values of y rather, are either less than -1 or greater than +3. Okay, now let's look at a real world type of problem. We all have smartphones, and we can see in this diagram that the operating temperature is stated to be between 0 degrees Celsius and 35 degrees Celsius. Well, we usually take our temperatures or work with temperatures in terms of Fahrenheit. So what we want to do is write and solve a compound inequality that represents the possible operating temperatures in Fahrenheit for the smartphone, because we want to make sure that we don't let the device fail on us. And then we're going to describe a situation in which the surrounding temperature could be below the operating range, which means it would fail, and then one which would be above the operating range, which means it would fail. So basically what we're going to do is we're going to write the compound inequality that represents the operating temperatures within which the phone will work. And then we're going to write another inequality, compound inequality, which shows the temperatures in which the phone might fail. Okay, so considering the information that was given, we know that our operating temperature for it to work is between 0 and 35 degrees Celsius. So this is a compound inequality. And so that would be the compound inequality in terms of Celsius, but we need to write this in terms of Fahrenheit. And then we're going to describe the situations outside the range. So that's going to be finding when it doesn't work. So our plan will be to include the formula that converts Celsius to Fahrenheit, because that's what we want to be able to do, is determine the operating system temperatures in Fahrenheit. Okay, so let's solve the problem, keeping in mind that C is Celsius and F is the temperature in Fahrenheit. So we have our inequality. 0 degrees is less than or equal to Celsius, which is C, which is less than or equal to 35. So these are the temperatures in terms of Celsius. Now we know the formula, or we can find the formula that converts Fahrenheit to Celsius, which gives us an equivalent statement that a degree Celsius equals 5/9 times the quantity a degree Fahrenheit minus 32. So C is equal to this expression, so we're going to substitute that in place of our compound inequality. So it gives us a compound inequality now in terms of Fahrenheit, which is what we're wanting to determine. Now we want to solve this inequality. We have our variable expression in the middle, so we're going to start undoing, and we have 5/9 times the quantity. So our first step would be to multiply the middle by 9 to undo the division, which means we need to also multiply the left and the right side by 9. And then we'll simplify the left, which becomes just 0. The right, the middle, the 9s cancel out. And then 9 times 35 is 315. Okay, then our next step here is shown to distribute, so that we can remove the parentheses. So 5 times f minus 5 times 32 is 160. And we need to continue to undo the operation so that we can get the Fahrenheit or the variable f by itself. So we're going to add 160 to all three components, add 160 to the left, to the middle, and to the right, and then we'll simplify. So we get 0 plus 160 is 160, which is less than or equal to 5 times f, which is less than or equal to 475. And last, we need to divide by 5. We're dividing by a positive number, so notice we did not reverse the direction of the inequality. And let's simplify. 160 divided by 5 is 32, which is less than or equal to, we simplify, we get f, and we simplify on the right side, we get 95. So our compound inequality states that the operating temperature for Fahrenheit is 32 degrees is less than or equal to f, which is less than or equal to 95. And that just simply means that as long as you are operating the phone between 32 degrees and 95 degrees, that is a safe operating temperature. So now let's consider the other conditions. The operating temperature is between 32 and 95 degrees. So let's consider a situation when it would not work. So a temperature when the surrounding temperature could be below this range would be possibly a winter in Alaska, and that's when it would be less than 32 degrees, and that would be a possible temperature it would fail. One situation when the surrounding temperature could be above the range is daytime in the Mojave Desert of the American Southwest, so greater than 95 degrees. So we can now also write a compound inequality that shows the values that do not fall in the operating range. In other words, this is the compound inequality that represents temperatures when it will not work. And that would be that if F is less than 32 degrees or F is greater than 95 degrees. So notice our compound inequality for the temperatures that do work was a compound inequality with and the compound inequalities that represents the values that do not fall in the operating range, which means it could fail, is an or compound inequality. This is the end of this video lesson for solving compound inequalities.